We already learned how to get the electronic configuration, the correct electronic configuration for any element. And today we'll talk about how to use this electronic configuration to understand and explain the atomic properties and the trend of atomic properties in the periodic table. We mean by atomic properties specifically four atomic properties. We are talking about an atom, so it's a nucleus uh, with electrons around it. So the first property is the size or the radius, the distance between the nucleus and the outermost electron, valence electron. That distance r is the first atomic property. It determines the size of the atom, the overall size of the atom. And then we have ionization energy, which is the energy lost or gained during the removal of one valence electron. And the third one is electron affinity, which is the energy required to gain one electron to the valence shell. And lastly, electron negativity, which is the relative attraction of an electron in a chemical bond between two different atoms. And we'll discuss each one of these properties and understand and explain the trends of these properties throughout the periodic table. First one is the atomic radii. And as we said, that's basically the distance between the nucleus, which is positively charged, and the valence electrons, which are negatively charged. That distance here is called d, is going to depend on the strength of the attraction between these two particles. We have a positively charged nucleus attracting a negatively charged electron. So the stronger the attraction is, the smaller the distance will be between them. If you have a strong attraction, that means the size will be smaller. And the charge, the strong attraction could result from a higher charge of the nucleus. So on the other way around, if you have a larger charge on the nucleus, that will cause the attraction to be stronger, which will cause the distance to get smaller. And that's exactly what happens as you go through the periodic table, through one period from the left to the right. As you go from the left to the right, the charge of the nucleus gets higher, which makes the attraction stronger and makes the size smaller. So that causes the size to go smaller as you go to the left. But if you go from the top of the periodic table downwards, the effect is going to depend on the energy level. Because, for example, period 1 corresponds to the filling of energy level 1. If you move to period 2, it's going to be energy level 2. And period 3 is energy level 3, and so on. So you're moving from one energy level to the next one. And as we learned during our discussion of the quantum model, the energy levels, higher energy level means higher distance from the nucleus, right? If you go from energy level 1 to energy level 2, that corresponds to higher distance from the nucleus. So as you go downward through a group, you're actually increasing the size. So in general, the size increases from the right to the left downwards. So that's a trend for the size, and that's the most important one because it's going to help us understand all the other properties later on. So let's just apply these concepts here to make predictions about the size. If you compare each two of these atoms here, which one is going to be larger? And remember, it all depends on the trend throughout the periodic table. So we will get a periodic table and locate each one of these elements and see how it compares to the other element in terms of the direction of increase. Increases from the right to the left downward. So anything to the left is going to be larger. Anything downward in the periodic table is going to be larger. So if you look at the periodic table, you will find that phosphorus is to the right with respect to silicon. So that makes silicon larger, right? And if you locate calcium versus cesium, calcium is on top, cesium is downwards. So that makes cesium larger. And then if you locate antimony versus lead, antimony is going to be right here in comparison to lead, which is both downwards and to the left. So that's again make lead larger. So C represents the set of the larger elements in comparison to the other set. Okay, and we'll quickly emphasize this fact here. The degree of size difference is more significant down the group in comparison to throughout the period. So you will find that nitrogen and oxygen are close in size to each other. So nitrogen is slightly larger, but not too much larger. While calcium and rubidium is all the way down the group. It's a higher energy level. So that's a significant change in size compared to the difference in size in the same energy level in case of nitrogen and oxygen. What about the size of ions? How the size of the different ions is going to compare to the parent atom and how it compares to each other. So if you look to the elements that become cations like metals, it's basically the parent atom itself is going to be larger because it will have the valence electrons, in case of lithium, for example, in energy level 2. But when it gets ionized, it will lose the electron in that energy level and goes to a valence shell that is energy level 1. So the size now is determined by the electrons in energy level 1, which are much closer to the nucleus, which means it's going to be much smaller in size. And it's also positively charged, which means the valence electrons now are attracted much more significantly than when it was neutral. So that causes the size to get even smaller. Okay? Same thing for something like beryllium. Again, in the neutral atom, the size was determined by electron in energy level 2, but when it got ionized, it gets determined by electrons in energy level 1, which explains the smaller size of the cation. And the cation gets even much more smaller because the electrons in energy level 1 right now feels much more stronger attraction from the nucleus due to the extra charge on the nucleus. Okay, so in general, all the cations are much smaller than their parent atoms. The opposite happens in case of the anions, because with the anions, the electrons are actually feeling relatively smaller attraction from the nucleus. Because, for example, if we are talking about oxygen had 8 positive charges attracting 8 negative charges in the neutral atom. So each electron in the valence shell, let's imagine it's feeling 1 positive charge. It's 8 per 8, right? But when it gets ionized, it's going to be the same 8 positive charges attracting 10 negative charges. In this case, the valence electrons are feeling much less fraction of the positive charge of the nucleus, which means it's gonna go a little bit further away from the nucleus and make the size go larger. Okay? So in general, all negative ions are gonna be larger than their parent atoms. Based on these two principles, let's think about this question right here. Just want to compare the size of neutral chlorine with negatively charged chlorine and positively charged chlorine. Order them in the increasing radius, meaning the smaller one first and then the next and then the largest.
Yes. I picked D because the Cl plus we said had a smaller radius because the N level is one less.
Yes, that's correct. Actually, in case of this specific example, it's not one energy level less, but still the valence electron is feeling more attraction because of the more positive charge on the particle, on the atom. Okay, but the argument is still correct. So keep going.
And then the second, or like the middle closest, I guess, would be Cl with no charge, and then Cl minus because it has less attraction to the nucleus.
Yes, thank you. That's exactly correct. So again, it all depends on the relative attraction between the nucleus and the valence electron. So as we said, in case of the positive charge here, it's going to be plus 17 charge affecting minus 16 electrons. So the valence electron is going to feel a little bit more positive charge than 1 plus, right? But in case of the neutral atom, is going to be plus 17 affecting minus 17, which means the valence electron is going to be feeling something around 1 plus, right? In comparison to plus 17 affecting minus 18 in the last case. Each electron is going to get a fraction that is smaller than 1 plus, okay? So it's going to feel a little bit smaller attraction than 1 plus charge. That's basically the same principle that we will use in all the comparisons that we will do now on in relation to the size or even other properties later on. It all depends on the concept of electrostatic attraction. So it's in all cases, you will need to think about the relative electrostatic attraction that the valence electron feels. And in most cases, when I will ask you to compare a couple of elements to get the larger or the smaller one, it will all depend on the relative attraction. So there will have to be something common between them. They will either have the same positive charge in the nucleus, so there are different ions of the same element, or they will have the same number of electrons. And in this case, they will be called isoelectronic species. So an isoelectronic species are any two or more species that have the same number of electrons, the same electron configuration, but different nuclear charges. So basically, ions or atoms of different elements. So, but the thing that is common between them is that they have the same total number of electrons. And based on that, the size will vary significantly because the relative electrostatic attraction will vary significantly. And we'll see this in the example here. So if we compare oxygen oxide ion with fluoride ion with neon, all these three species have a total of 10 electrons. but the nucleus of each one of them has completely different number of protons. So you can see that the 10 electrons in all cases is gonna feel a different degree of electrostatic attraction. In case of neon, is gonna feel the maximum electrostatic attraction because it feels the electrostatic attraction of 10 positive charges in the nucleus. But when you go to fluoride, it feels slightly less attraction because the number of positive charges is smaller. It's now 9. So that's why the size is slightly larger. And as you go to oxide, size is even larger because the attraction that the electrons feel is even smaller. So let me ask, what about if we want to place something like sodium or something like nitride? How many electrons does these two species have? How many electrons does a sodium atom have, a neutral atom?
Would it be 11 for a neutral atom?
For the neutral atom, it's 11 because the atomic number is 11, right?
Oh, right.
Atomic number is the number of protons or the number of electrons in total. Okay?
Okay.
So when you make a 1 plus charge, how many electrons it will have? 1 plus means that you removed 1 electron. Okay? So how many electrons it will have?
So I have 10.
It will have 10. That's correct. Okay. What about nitride? Nitrogen with 3 minus. How many electrons does a nitrogen atom have? 14 is the weight, but the atomic number is 7, right? So 7, but you have 3 minus charge, so that's gonna add 3 electrons. So this species also have 10 electrons in total. So both of these species are isoelectronic to what we are discussing right now, the series that we are discussing right now. Both of them have a total of 10 electrons, okay? Thank you, George. Knowing this, if we want to place each one of them, where it will go? Is it gonna be larger than oxide or smaller than neon? Let's start with sodium, for example. Are you expecting sodium to be larger than oxide or smaller than neon?
Could you say the question one more time?
If you want to compare sodium ion in size with neon, fluoride, and oxide, is it gonna be smaller than neon or larger than oxide?
I think it's going to be larger than neon.
Larger than neon? So
yes.
it's gonna go here?
Yes.
Why do you think it's gonna be larger than neon?
Actually, I think it's going to be smaller because going by the trend, it should be smaller than neon.
Why?
It has more protons, so the attraction is going to be much greater.
Thank you. That's exactly correct. You have more protons, you have more positive charge, so the attraction the 10 electrons will feel is going to be much larger than neon. So the size is going to be smaller. Okay, thank you. What about nitride? Is going to be smaller than neon or larger than oxide? How many positive charge does it have?
It has 11.
For nitrogen, it's a nitride ion.
So 10.
Can you bring up a periodic table in front of you? What's the atomic number of nitrogen?
Nitrogen is 7.
7, which means how many protons does it have?
7 protons.
So proton is 1 plus. So how many positive charges?
7.
7 plus. And how many negative charges, like in total number of electrons? We just calculated this. It's going to be 10. So how's the attraction between the 10 electrons and the 7 protons compared to the series that we are looking at right now?
It's going to be larger than the oxygen.
Yes, it's going to feel smaller attraction because of the smaller number of positive charge. So it's going to be larger in size than oxygen. In all cases, it's the same argument. We're talking about the relative electrostatic attraction that the valence electrons are feeling. And that is going to be the basic principle that we can use to compare two different species. Whether they are having the same number of electrons and varying protons in case of the isoelectronic series, or the other way around, if you're comparing a neutral atom to its positively charged ion or negatively charged ion. Okay?